Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In this lesson, we're going to look at electrolytic cells. Now, electrolytic cells have a lot of things in common with voltaic cells, but they do have some major differences as well. So, starting with similarities, we still are using our acronyms, jerk OA or LEOA RA. We're still using A to A, anions move to the anode, C to C, cations move to the cathode, and of course ACE, anode to cathode move electrons. But there are some pretty significant differences. An electrolytic cell is non-spontaneous. Now, a voltaic cell is spontaneous. What this means is we're getting an electric potential which is going to be negative. And we are not producing electricity, we're actually consuming electricity. So in an electrolytic cell, we're taking electric potential energy and we're turning that into chemical potential energy. Also, there are no half cells. So those are some pretty significant differences. But because we're using so many of these acronyms and we're treating so much of this the same, it won't take as long to develop an understanding of electrolytic cells as it did for voltaic cells. So we're going to dive right into looking at the cell notation for an electrolytic cell. So here's our example. What you'll notice is there's no double slash. So in a voltaic cell, you have something, which is an electrode, an anode. Then you have an electrolyte, and you have a double slash. This representing the porous cup, porous membrane, porous barrier, salt bridge. Then you have another electrolyte, and you have the cathode. Here, all we have are these two slashes. This, of course, being on the left-hand side would represent our anode, and on this side it would represent our cathode. Now, a lot of the time, our electrodes are inert. So we'll see a lot of questions with platinum or carbon as the electrodes. Now, the part through the middle is still our electrolyte. Now, we absolutely have to do a species list here. So once I've figured out what I have, I'm going to make a species list. I'm not going to include the platinum in the species list because I know that it's an inert electrode. So I would simply have copper 2 plus aqueous. I would have nitrate ion aqueous. And I would have water. Now, copper 2 plus is an oxidizing agent. Nitrate on its own is neither an OA or an RA. If this was acidified, of course, nitric acid would be an oxidizing agent, but we don't have that here. And then water can be both an oxidizing agent and a reducing agent. Now, we already know what the SRA is because we only have one option. So I know that water is going to react at the anode because it will lose electrons, undergo oxidation at the anode because it's the reducing agent. Now, out of water and copper 2 plus ion, copper 2 plus ion is my SOA. It's at positive 0.34 volts. Water as an RA is actually at positive 1.23 volts. And so I know that the copper 2 plus ion is going to gain electrons and undergo reduction at the cathode because it's the oxidizing agent. So I have a general idea now of what's going to go on which electrode. So I'm going to focus on the diagram now and talk about how I'm going to set this up. The big difference you'll notice is there's no voltmeter here. I have to have power of some kind. So there's no voltmeter, no light bulb, no multimeter in the middle of the wire. We have to have power. Now, completely at random, I've just decided that I'm going to call the left electrode the anode, and I'm going to call the right electrode the cathode. Something that you need to know is that you don't need to know which electrode is positive or negative. All we need to know is what's the anode and what's the cathode, and because this is my own drawing, I can determine which side is which. I'm just choosing to have the left side as the anode, and I'm choosing to have the right side as the cathode. And because the platinum is inert, it doesn't really matter which one I put where. Okay, the next thing I'm going to do is I'm going to add our electrolyte solution. So I've got copper 2+ ions, aqueous, and I have nitrate ions, aqueous. And of course, because this is aqueous, there's really water everywhere. So the next thing I'm going to do is stick with all my flows because we have to do that for all of our questions. So I'll start with ACE. From anode to cathode, move electrons through the wire. Then we know C to C, cations move towards the cathode. And we know A to A, anions move towards the anode. So all of our flows are done. The next thing I'm going to do is I'm going to write out the reaction that occurs at each electrode. So I know that copper 2+ reacts at the cathode and it's gaining electrons there. So I look up the half reaction and I get copper 2+ plus 2 electrons becomes copper solid. And then I go and I look up water as a reducing agent, which is at positive 1.23, and I write that reaction reversed because this is an oxidation. So we have 2 H2O liquid producing O2 gas plus 4 hydrogen ions and 4 electrons. In order to balance this reaction out, I would have to multiply the copper side by 2 in order to get 4 electrons so that the electrons would cancel out. The next thing we're going to do is we're going to focus in on each electrode and the evidence that we would see at each. So I notice that water is turning into oxygen gas. So on this electrode we would see bubbles forming, and those bubbles would be oxygen gas. We are also producing hydrogen ions, which are acidic. So the pH at this electrode is going to start to go down. Eventually those hydrogen ions will move throughout the entire solution and the entire solution will get quite acidic, but it depends on how long you leave that electrolytic cell running for. What you will also notice is we don't have a solid turning into ions, so this electrode will not lose mass. Again, if you're going to lose mass, it's going to be at the electrode, at the anode electrode. But I have no solid in this half reaction turning into aqueous ions. When we go to the other side, we'll notice that copper 2 ions are turning into copper solid. So we're going to have a gain in mass, and this electrode is going to get bigger. Now, nobody would actually coat platinum with copper. It's just a theoretical cell, but we can see that change. The other thing we'll notice is that copper 2+ is blue in color, and if we're consuming it, it's going to start to get less blue. So this entire solution will start out some shade of blue, and as those copper 2 ions get used up, it'll become less and less blue. Now, it could go completely clear if you leave it running long enough and all the copper 2 ions are consumed. The next thing we could do is we can make a net reaction. So because we've already balanced out the electrons, I can start putting the reactants together and the products together. So this would be 2 H2O liquid plus 2 Cu2+ aqueous would turn into oxygen gas plus 4 hydrogen ions aqueous plus copper solid. Now we need to check to make sure that the charge is balanced. So looking at here, I got 2 times no charge is no charge, 2 times 2+ is 4+, nothing times 0 is 0, 4 times 1+ is 4+, and 1 times no charge is no charge. The grand total of charge on the left is 4 plus, the grand total of charge on the right is 4 plus, so I know I balanced this correctly. The next thing I need to do is the electric potential of the cell. So it's going to be the electric potential at the cathode minus the electric potential at the anode. And so I've got a positive 0.34 volts minus a positive 1.23 volts, which gives a grand total of a negative 0.89 volts. So you'll notice that we have a negative electric potential, which means this is non-spontaneous, that it means that it's consuming electricity, and it's turning this into chemical potential energy. So that's our question as a whole. One thing I always get at the end of a question like this, which we never discussed at the beginning, is when you look up on your reduction half reaction chart, water is above copper 2+. And students quite often say, well, this is non-spontaneous. This doesn't even work. And the answer is, it doesn't work unless I give this cell power, which I have. This power forces the non-spontaneous reaction to happen. So the next thing we'll do is have you try a question, and I'm going to guide you through it step by step. The first thing for us to do, though, would be to pick a couple of electrodes. So I'm going to say that this is a carbon inert electrode, and we'll call it the anode. And I'm going to call this one carbon as well, inert electrode, and I'm going to call this one the cathode. I'll put an electrolyte in this solution. So I'm going to call it sodium bromide. And so the first thing we'd want to do is make a species list and figure out what our strongest oxidizing agent and strongest reducing agent are. So pause the video, make your species list, and figure that out. Now that you've had a chance to do that, let me go through it with you. So since this is an aqueous solution, I have to have water. I also have the sodium ions, aqueous, and I have the bromide ions, aqueous. Now water could be an OA, or it could be an RA. Sodium ion is an oxidizing agent, and bromide ion is a reducing agent. So when you look at your reduction half reaction table, your strongest oxidizing agent is going to be water, and your strongest reducing agent is going to be bromide. Now, bromide is much higher up the table than water. And again, a lot of students would go, well, this is non-spontaneous. It doesn't even happen. Again, that's the whole point of having the power supply. The power supply will cause this non-spontaneous reaction to happen. So I know that we are going to gain electrons and undergo reduction at the cathode, and the species that's going to do that is the oxidizing agent, which is water. Now, I also know that the bromide is going to lose electrons, undergo oxidation at the anode, because it is the reducing agent. Okay, the next thing I'd like you to do is your 3 types of flows: anion flow, cation flow, and electron flow. Pause the video now and do the 3 flows. Now that you've had a chance to do that, let's see if you got it right. So starting with electron flow, from anode to cathode move electrons, or ACE. Cations move towards the cathode, and anions move towards the anode. The next thing I'd like you to do is write the appropriate half reactions beside each half cell and do the evidence that you would see. Pause the video now and do those 2 things. Now that you've had a chance to do that, let's start at our anode. So starting at the anode, I have 2 Br minus aqueous turning into Br2 liquid plus 2 electrons. Now, bromine, Br2, is a liquid at room temperature, and it's going to be brown in color. So it's that orangey brown, reddish brown color. So the evidence that I'm going to see is kind of like a orange brown color or a reddish brown color forming around that electrode. And that's it. I don't have any other thing going on here. I don't have a solid becoming aqueous. I don't have acid or base being made. Now, this is something that you do have to remember. Bromine is, sometimes they say it's a yellowish brown, orangish brown, reddish brown, something like that. It has to be memorized. Going over to the cathode side, I have water reacting at the cathode. Now, this isn't the same half reaction that we had in the previous question. In the previous question, the water was the reducing agent. In this one, it's the oxidizing agent. So water as an oxidizing agent is a little bit different. So it's 2 waters plus 2 electrons. This is going to form hydrogen gas, and it's also going to form hydroxide ions. So there was a gas formed in the previous question, but it was oxygen. In this case, it's hydrogen. So I'm going to have hydrogen bubbles building up on the cathode, and they will bubble out of solution. And then I also have hydroxide ions forming, which are basic. So I know my pH is going to increase and become more basic. I don't have any loss of mass here or any other color changes. So those are the 2 pieces of evidence I see in this side. Okay, the next thing I'd like you to do is I'd like you to make a net reaction and calculate the electric potential of the cell. Pause the video now and give those 2 things a try. All right, so now that you've had a chance to try that, let's see how you did. The first thing I notice is this is 2 moles of electrons on both sides, so those will cancel out nicely. I can just put the reactants together and the products together, and I'll have my net reaction. So the net reaction is going to be 2 Br minus aqueous plus 2 waters. This is going to turn into Br2 liquid plus hydrogen gas plus 2 hydroxide ions aqueous. Now we should check our charge. So 2 times -1 is -2. 2 times nothing is nothing. 1 times nothing is nothing. Nothing. 2 times -1 is -2. The grand total over here is -2. The grand total over here is -2, and I know I balanced it right. In order to calculate the electric potential, we have to go cathode minus anode. So the electric potential at the cathode side minus the electric potential at the anode side. So the cathode being water, or I should say the substance that reacts at the cathode is water, and its electric potential as an oxidizing agent is a negative 0.83 volts. And I'm going to subtract from that a positive 1.07 volts, which is for the bromide. And when I do that, I get a total of a negative 1.90 volts. Again, I have a negative value here because it is non-spontaneous. And so this would be called the minimum voltage to get this reaction to occur. So stepping back from the question, those are all the things that you could be asked to do in solving for this electrolytic cell. The next type of cell we're going to look at is a molten cell. Now, whenever you see the word molten, you need to have your brain scream at you, there is no water. This is not an aqueous cell. A molten cell is when you melt an ionic compound into a liquid inside of the cell. So this is done at very, very, very high temperatures. Now, if you're wondering, why would I want to melt something and not just make it an aqueous solution? The reason for it is if you want to purify metals that fall below water on the reduction half reaction table, there cannot be any water. So let's go to our reduction half reaction table and I'll show you what I mean. So let's say I wanted to purify sodium ions and I wanted to turn them into sodium metal, and I want to do this in an electrolytic cell. I couldn't have it in an aqueous solution. The reason for that is water's here, and of course aqueous means it's dissolved in water. So if I was to make a species list, water would be my strongest oxidizing agent and sodium would never react. I also wouldn't want to produce sodium metal in water because it would just explode. So there is no such thing as a aluminum mine or magnesium mine or sodium mine or calcium mine in terms of digging up pure aluminum metal, magnesium metal, sodium metal, etc. because these readily react with water in nature and they turn into ions. So when we have a magnesium mine or aluminum mine, really what we're doing is getting the ionic salt of aluminum, or literally salt if you're talking about sodium. I could use sodium chloride in this type of cell. So in order for an electrolytic cell to work, you need to have ions, you need to have an electrolyte. So an electrolyte has to allow the flow of charge. And solid ionic compounds are rigid, the ions can't move, and so it's not an electrolyte. But if I melt it down, I turn it into liquid ions. Now that is an electrolyte, it's just a liquid electrolyte. So if I don't have any water here, and I have liquid sodium, then I could force this reaction to go forward, and I would actually make liquid sodium, which would then be cooled down and turned into bricks of sodium which can be sold. This is a very dangerous process. It has to be done at very high heat. It has to have no moisture in the air, no oxygen in the air, or it could cause an explosion. So let's go back to our notes and finish off the question. So let's design a cell that is going to purify salts. So my species list would be sodium ions liquid and chloride ions liquid, because I'd use standard table salt, sodium chloride. What you'll notice is there's no water here. So in the question, it would be very clear that this is a molten cell, and they could show that by saying the word molten or actually expressing it in terms of the ions being in the liquid form. Now, this leaves me with only one oxidizing agent and only one reducing agent. Therefore, the sodium ions have to be the strongest oxidizing agent and the chloride ions have to be the strongest reducing agent. Just to keep things simple, I'm going to call this platinum. I want an inert electrode, something that's not going to react. I'm going to call this side the anode. Over here, I'm going to keep this as a platinum electrode as well. It's an inert electrode. I'm going to call this the cathode. And then, of course, we need to put our liquid ions into the cell. So I have sodium ions liquid, and I have chloride ions liquid. If we do our flows, electrons always flow from anode to cathode. Cations move towards the cathode, and anions move towards the anode. The next thing I do is I look at my two half reactions and write them out as they appear. So the sodium one, of course, is the reduction half. I'm going to write that out exactly the way it appears in my reduction half reaction table, making sure to write that this is liquid. Now this is plus an electron, making sodium. And you could put solid or liquid here. It would eventually be solid once they cool this system down, but this would be done at hundreds of degrees Celsius, so it would still be liquid at the cathode. Now going to the other side, I've got chloride ions. So this is going to be 2Cl minus liquid. I know it seems weird to do that. Now this is going to turn into chlorine gas. It is going to be a gas because it is so hot. Chlorine is a gas at room temperature, so at hundreds of degrees it is going to be a gas, plus 2 electrons. In order to make sure that this is balanced out properly, I would have to multiply the second reaction here by 2 to get 2 electrons, so the electrons cancel. So on the anode, I would see the formation of a gas, chlorine gas. It would smell like a pool, and that's all I would see there. On the cathode side, I would see the formation of liquid sodium metal. Now this would get piped off and then put into bricks and allowed to cool. And it has to be stored in, again, oxygen-free, moisture-free, because sodium metal is very explosive. Now, the next thing I'm going to do is make a net reaction. So combining the two, I've got 2Cl minus liquid plus 2 sodium ion liquid turns into Cl2 gas plus 2 sodium liquids. I'm not going to calculate an electric potential for this cell because the electric potentials from the reduction half reaction table in our data book are set to 1 molar aqueous solutions, which we don't have, and at 25 degrees Celsius, which this wouldn't be at. So you will not be asked to calculate an electric potential for a molten cell because we do not have the electric potentials to do so. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.